Alright, well clearly windowing has some effect in the frequency domain, and there are two main effects. Of windowing. Let's see, I better spell that correctly. Okay, the first one, and these are quite related. The two are smearing and the next one is leaking. And it sounds kind of disgusting, but these are the terms that people use. First we'll look at smearing. Okay, and the idea is if we have a spectral line from a sinusoid, what we actually see when we observe it in a finite time window is we see this sinc function. Okay, so this is x windowed e to the j omega. What has happened is this infinitely narrow spectral line is now spread out. It's smeared out over a wide range of frequencies. It begins, all of its power is concentrated at a single precise frequency. But after we observe it, the frequencies are, the spectrum is smeared out over a range of frequencies. It's still centered at omega naught, but now it's smeared out. This leads to a loss of resolution. Oops. What I mean by a loss of resolution is that we lose the ability to detect if there are actually two lines or more lines present. As you can imagine, if there are, say, a line here and a line here, and we observe it over a finite time period, what we're going to wind up with is two sinc functions, that one and then one right next to it, and actually what we see are not those individual ones, but we kind of see the superposition, the addition of both of those things. So this is what we see. And we've lost the ability to resolve these two lines. Okay. So that's the smearing effect, and what we can do to help that is increase the number of samples observed, and that reduces or narrows the sinc function, so there's less smearing. We'll talk more about this in a minute. Okay, the other effect is, okay, smearing has to do with the idea of resolution, the idea that if we want to detect two lines that are close together, we're going to have to deal with this smearing thing. The next one is leakage. Leakage is really the result of side lobes of the sinc function. So, for example, if we have a line there and a spectral line there, this is in the original signal, and then we observe it through n time samples, so that we actually get what we actually observe looks like Well, we get a sinc function there at omega 1, so that's at omega 1. But look at this low level sinusoid at omega 2. It's going to look like this. Now the problem is that you see these side lobes. That there is referred to as a side lobe. These side lobes of a sinc function are actually pretty big, and they can be as big or bigger than an actual main lobe that's due to a spectral line. So the idea of leakage, it means that power in the original line leaks into these side lobes. And these side lobes make it difficult to detect small spectral lines. Okay, so difficult to detect low amplitude lines in the spectrum. I'll call them signals, due to strong side lobes. In fact, when we look at these spectra, we see all these side lobes, and we don't know which. We see all these bumps in the spectrum. We don't know which of them may be due to real signals that are in the original signal, or which are just side lobes, that an energy that's leaked out of the main frequency. So as an example, suppose we have two sinusoids. And they're very close together. 2 pi over n and 3 pi over n are their frequencies. How many samples, n, do we need in order to resolve these two lines? So that's the question. The thing of interest here is what the distance is between these in terms of frequency, and I'm going to call that delta omega. So delta omega is taking different meanings as we go through the lecture, but right now delta omega is going to be the difference between these two frequencies. So we got 3 pi over 10 minus 2 pi over 10, which is pi over 10. Okay. We need this delta omega to be larger than the sinc function lobe is. In fact, and I'll make this argument that if delta omega is about 1/2 of the main lobe width, then we should be able to see both lines. No guarantees. But that's my argument. And the reason for that is that if I have a sinc, so here's the two lines. Here's the two sinc functions. If this is one of them, and this is the other of them, as long as the distance between them is about half of one lobe, here's one lobe width from there to there is a whole lobe, but you know, if the separation is just 1/2 of that, we should be able to see the presence of the two lines. So the distance, if you remember a Dirichlet function, the distance between the top and the first zero crossing is 2 pi over n. That's this distance. I'll make it in like green color. That's the distance between here and here is 2 pi over n. That's also the distance between here and here, although they're not drawn to scale. Those are all in between there and there. Those are all 2 pi over n. Okay, so we need W2 minus W1 approximately equal to 2 pi over n. Okay, separation of two lines, 2 pi over n. So that means n should approximately be equal to 2 pi over omega 2 minus omega 1, where that's omega 1, that's omega 2. Now, for example, in our case, omega 2 minus omega 1 was pi over 10, and if we plug that into this formula, we get that n is about 20. So we need about 20 samples of this signal here in order for us to resolve the two spectral lines and see that there's two frequencies. Now, this is really kind of a rough rule of thumb. It means that n could be larger or n could be smaller. It depends, and we're going to do some trial and error if we really want to get the exact number, which we sometimes do. So if we want a closer estimate, we just have to plug it in and have a look at it. And that depends, you'd think we'd have a more accurate number, but it depends on the phase. There's phase here, and these lobes constructively and destructively interfere with each other, and it depends on the relative heights. If one cosine is bigger than the other cosine, or one's a sine and one's a cosine. You'll see, I'll give you a homework problem and you'll play with it, but you'll see everything changes a lot. So this is a good rule of thumb.